Hey folks, it's George Leoniak and welcome to New Geometry. Today I'm going to do a video that's going to be a little different than just a regular presentation because I'm kind of working through trying to discover more about the relationship between, or the presumed relationship between phi and pi. Now, I did a recent video on the Great Pyramid, phi, pi squaring the circle, so you may want to refer to that first just to get familiar with some of the things I'll be talking about. Definitely not necessary because today I'm going to kind of walk through some, basically a kind of test that I worked on to see if pi is related to phi. And really, we're going to be talking about the values of the standard pi, which is 3.141. That's where I'll take it to. And the golden pi 3.144. So really it comes down to the digit of 1 and 4 at the end of that sequence. So either 3.141 or 3.144. Now, there's been a little flurry of activity on my Facebook page from one person named Lids, and they shared some information that I want to share first to discuss this person, Harry Lear's website. So let me share that. And then we're going to also go through to the iPad where I kind of constructed some possible tests for this. And then we'll look at some of the values of it on the Geogebra program. So this is really kind of meant to be a kind of exploration. And definitely I'm not trying to come up with the value of pi here. I'm trying to decipher whether the true value of pi is closer to 3.144, the golden pi, or the standard value of 3.144. So this is the website measuring pi squaring phi, and this fella, Harry Lear, has done a kind of tremendous amount of work working with the golden pi to actually measure this with physical instruments rather than just working on a computer like I'll be showing you here in a moment, or on the Geogebra program and the iPad. But as you can see, I'm not going to go through any of these videos. You can definitely check them out on your own. What he's done is he's basically using like a 1 meter length diameter for the circle. So he's using a 1 meter diameter, and that's going to, of course, have 1,000 millimeters within that. And then he's going to, run a tape measure, flexible bendy tape measure around the circumference of that, and he's going to come up with a value by doing so with the actual physical materials of 3.144, roughly 5. So, he documents this all here. And just to let you know, I'm not lobbying for one pi or the other here. I'm just super curious about this because I think it's an important subject that may not be for everybody, but it would be very interesting. And of course, I would think it would be grand and fantastic if the value of pi was related to the golden ratio, because that means we could do great squaring the circle drawings and it would just fit seamlessly in with so much more of the other sacred geometry content and drawings that I've shared related to the golden ratio on this channel. Okay, so like I said, we're going to hop around. This is not like one of these fully baked presentations. I'm just going to kind of wing it here and talk to you about what I did to kind of look at kind of using some of Harry Lear's ideas and see if I can replicate that, because I don't have all the precise equipment that he has to do that. But is there a way that I can somewhat replicate this, but it's going to have some slight issues because I don't have a circular tape measure or a circular way of measuring the circumference of these circles, because these programs like Geogebra, of course, would all be working with the value of pi. But let's just see what I came up with here. So just kind of go with the flow on this, and don't jump if you're a strong advocate for the golden pi. Just follow me out here because I'm really just exploring this as best I can with the limited tools. And I'd love to know your thoughts on why my way of doing this is flawed, and Harry Lear's method is correct, and the true value of pi is the golden pi. But let's at least walk through what I've done here to just get the conversation going in a way that looks at another possible way of figuring out what the value is closer to, basically golden pi or true pi. So, all right, this diagram I'm going to kind of zoom in and out of here for a moment, but on the program Euclidean Sketches on the iPad, which I use for all my drawings that I set up and do pretty much, it's great, super precise, works. Double checked it with Geogebra measurements. And here I do have a circle around here. But this program doesn't actually give me any values other than, just an angle measurement is the only real value. And it could tell me that lengths are the same, but it doesn't go past the 1 digit of precision, beyond the decimal point for that angle. So I'm not really worried about all that here. What I did basically was I basically am going to kind of try and see if I can replicate Harry Lear's study, but it's already going to be a little different because, of course, I can't take a tape measure and go around the circumference of this. But I did create a diameter here of 1,000 units. Okay, so if we zoom way in over here to the left-hand side, you'll see that I have 10 little units here. These little white dots, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way across here from the starting the black dot. And once I had that 10 units, of course, I just, like using a compass, this would be what you'll see in Geogebra in a minute. This, I don't have to make circles to do this. I just go along, and I'm going to basically create, a group of 10 of those, right? So then we're all the way out to here, and then I'm going to replicate that. So we're going to have 10 of those larger units, which this whole thing is going to add up to 1,000 of those tiny little units along this whole length until we get to the other side here. So there are 100 units in this little section. So there's 100 units between each of these white little nodes going along the length here of this whole thing, equaling 1,000. So, this is, and you'll see the values of this, at least as best I can do in Geogebra. But what I did was, okay, this is the best I could do on the program here, was let's just see what happens if I take the length of this short little segment, which is pretty tiny, this 1 unit of 1,000, and I decide to move it all the way up to the top of our circle here, up top at the apex. And then I just, I'm going to just rinse and repeat. I'll do it with circles so you could see, working my way around the circumference of the circle. Hold on a sec here. Let me just grab that in the right spot. So I just keep working my way around like so. Whoops, I'm doing this a little rough and fast here. Until I work my way around, until I hook up with all these, and you can see that would be another grouping of 10. Now, this length, of course, is not going to be the same length as the group of 10 down below. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But what I did here was, I'm just going to repeat that unit of group of 10 out to here, 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 those little white dots. And you see then I'm going to go out to a group of 100. And then once I get to a group of 100, I'm going to replicate the group of 100 by going around 100, 100, 100, all the way around until I get to the 1,000 mark. So this right here would be 1,000 of those little units till I get to this point. And then I'm going to swing it over here to 1,000 of these units, 1,000 of these. And then at that point, I'll have 3,000. So this black dot right at the top here is 3,000. So I take 100 units and move it over to here. And then I'll take 40 more units, which is this segment from here to here. So we got 40, and then I zoom in a little bit further, and I'm in the kind of end game here of what happens in the last little sequence because I'm already at 3,140. So remember, everything here for the value of pi is going to be multiplied by 1,000. So instead of thinking of 3.141, just think of 3,141 or 3,144. So I'm at 3,140, and I'll take one of those short little units, the starting units that I have here, these circles. Let's get rid of those because they're a little in the way. And I'm just going to put one more segment down, and I'm at 3,141 of just walking around with that circumference. Now, what we really want to know is what's the difference, and I'll get to this in a little bit as best as I can. What's the difference between the length of the arc above it, right, the true arc, compared to the length of that segment? Because if that is a really big difference, then of course the segment length is going to be much longer. It's going to the segment length would be, there'd be such a difference between those, I wouldn't end up being close. So we really want to try and determine what the arc length is as best we can, and I can only do that in GeoGebra using the standard value of pi, but I'll show you what the numbers are there in a moment. But anyway, I'm at 3,141 units. So then I'm going to extend another unit beyond. So I'm at 3,142, 43, and here's 3,144. So that goes way beyond our starting point to get something that would be related to golden pi based on this kind of analysis that I'm doing here. Now, it's interesting on the Harry Lear's study that he did with the actual physical measurements of, he actually came up with, the 3,144 point, or 3,144, yeah, 0.6, of course, being right here at the vertical line. So when I did this, I was really surprised that as I stepped my way around that I overshot it by this much. Because I didn't think there would be such a huge discrepancy between the little bit of arc length here and the segment length. Because as you can see, and I'm already at my max zoom extent, but I can show you in GeoGebra, if I do just take one of these short little segments and I swing it up to the line there, and I try to zoom in. I'm already at the max extent, but I can't right now tell the difference between where the line and the actual circumference of the circle is. So I didn't think it would be a huge difference there. Okay, so that's just a very crude example or crude way of how I did a kind of trying to test this out to see if I'm coming up with something close to 3.141.5. Which, remember, there is this little remainder here past the 1. So here's 3,141, and then this bit, which is just about halfway. So it is roughly about 0.5 beyond in our study, in this kind of study. All right, so I'm going to go over and let me just show you this same slide, just with some of the numbers, because it may get a little confusing with me zooming in and out there. But I'll share the screen of an image in my photos where I was able to write up some of the information on here. Now, of course, this also has the angle of the Kepler's triangle, 51.8273. I decided to take that out because it really doesn't add much to what we're studying here, because we've already determined we're dealing with 1,000 unit diameter here. So I have here that the circumference is going to roughly be 3,140 plus, and that plus is that we don't really know what happens at the end here. So as I did this study here, just walking through this one more time so you see the numbers, is 1,000 units of those little tiny units that I showed you from way down over here, going all the way over to here, another 1,000 to here, another 1,000 to here, 100 to here, and 40 to there. and then we have that little remainder at the top. So at that point, we have 3,140 little units, and then we get to the top of the drawing, and this is what we come up with here. So I'm saying there's 3,140 of these tiny little units, which are this length, and then I go to 3,141. Here's where we started, which is roughly going to be 3,000. It's going to be a little bit beyond 0.5 of the length of this next unit, 3,142, 43, and up to 3,144. So this is really giving me a lot of different results. And of course, I didn't have any way of calculating the circumference of this circle to say that what the measurements are here precisely. I just took a 1,000-unit diameter and just made a circle and just started working with that little diameter, that little unit all the way around. And this is what I came up with. Now, like I said, it's not super precise to do it that way, but there are 3,000 little units. And of course, there's a lot of argument for the true value of pi because we're not accounting for that space above this polygon segment. Now, supercomputers, I guess, I don't know how they really calculate it, but even when ancient Chinese did this with 12,000 sided polygon, they still got very close to 3.141. And what they got 3.141. They got that, and then they were just trying to refine the digits beyond that. So they were already over here at refining the digits with the 12,000 sided polygon. So how much does that little distance between the segment length and the arc length make a difference between adding that by adding that much of a difference to the value of pi that we haven't accounted for that the true value would be 3.144? I'm not sure. I'm a little confused how that would work out at this point. But the fellow Harry Lear shows that with his physical tape measures that it did end up that way. So that's probably going to be my next step, is to try it that way. But let's hop over to Geogebra and let's just take a look at some of the numbers associated with this. Now, as I said in my last video, that I don't think Geogebra could ever really be used to help us solve this problem, because it's always going to calculate the value of pi as standard pi. So I got a lot of mess of numbers up here. Don't worry, we're going to zoom into all that. But this is basically replicating what I just showed you. And I have a bunch of circles on here because the compass tool just creates circles. And so these are the same thing I basically did. Just started with 1,000 units, made the circle, right? So this is basically representing a diameter of 1. So if you have a diameter of 1, just, not 1,000. If you have diameter 1, plug it into your, in your calculator. If you hit pi, that'd be 3.1415926. So if you've got that, that means that circumference would be equal to a circle that has a diameter of 1. So remember, we're dealing with 1,000, then we just multiply pi by 1,000 and we come up with 3,141.59. That's what the calculator would say. Okay, so this is the same thing. I don't have to step through all this because it's going to be tricky zooming in and out here, and I don't want to give you motion sickness while I do this. So I'm just going to zoom into the part that really matters, so these numbers all kind of separate, because we're zooming way back in to the end point of what's happening when we finally get to where the circle is coming, the circumference is coming to the end point here. So, okay, there I am, way down in there. So this is a little unit ones. Let me separate everything out so I get all the text, because I had to type some notes in here, at least the values. So a lot of numbers on here to walk through. And of course, I'm already limited here with, sorry, I got a call coming in. I'm already limited with the true value of the standard value of pi here, but this is what I wanted to really test out here. Okay, so this is what this is all going to be about. So let's say I went around with my arc with my length here, right? I'm just adding up the values as I walk my way all the way around. That should be when I get all the way from the center point D all the way back to P1, I should come up with 3,141, right? So if I take the value of the arc length of measuring in GeoGebra, this arc from D all the way to P, which is basically the red line that would go all the way around, come back to P1, the arc length there is up to that same point where this circle ends. And I don't have all the little circles here, but this is the same end point if I just continue these little circles all the way around to P1. The arc length it gives me is 3140.00052333968. Now, interestingly, if you do, and I did set the decimal point to 10 here, 10 digits beyond the decimal point, because if you do extend the digits beyond, just in case you did this on your own, you'll notice that where the value of 1 here, it's like 1.000000, and then some numbers way down at the side. I basically rounded up because those digits are way back over here, past the 7. And I recalculated everything just to see if that would make a difference in any of these numbers, and it really doesn't. So I just wanted to deal with, okay, we're at 1 here, and whatever GeoGebra is doing with the last remainder of these digits that are way here, or what that little, why it's not 1 precisely anymore, I'm just going to say, I don't know. But I don't think it's going to affect what I'm showing here. So, okay, let me just describe. So we got 1. So the unit lengths here are all 1. So this should be 3,141. So the arc length here is 3,140, 00523. All right, so what I want to do here is then I want to measure the arc length of the remainder here, which is the portion that would be 1. Okay, so P1 to Q1, that arc length, which is the arc length right above 1. Okay, so that's what we really want to know is, what is this arc length above 1? What's the difference? Is it a really huge difference? Well, that arc length above that is 1.000000, should be 6 zeros, 1667. All right, so that's that little bit of arc length that's just above the section of the circle cutting the circumference there with the 1 units, right? So that's not a huge difference between the unit 1 and the arc length above it. And then we got this little bit of remainder here, this Q1 to D1. Now, Q1 to D1 as the straight line measurement is 0.5921299917. And the arc length that I get there, which is now taking the measurement from the circumference of the circle, is 0.5921300263. Now, just remember, all these values of the arc lengths, they're all based on standard pi. So that's all I have to work with. I can't check the golden version of it. But all I can check here is that I've walked, what I do know is that I have walked around this whole thing with that 1 inch or unit 1 small little segment, that all the way around till I get here, and I'm coming up with a comparable number of 3140 arc length compared 000523 arc length compared to 3140 dead stop. Okay, so I want to just talk about some of these calculations up here. And so what I did was I took, and I can't do the subscript here, but H3 plus P3, which is this arc length plus this arc length. And, oh, did I mess up on that calculation? Maybe I forgot to add that. Oh, no, sorry, I did add that one in. I added in 3.141. That should have that 1 in there. So what did, oh yeah, that's right. Sorry. Bear with me. Okay, so 3140.00263 0.0. Okay, so yeah, when I add H3 plus P3, so that's this number plus this number, I come up with 3141.005235. And then if I add up this arc length, which is this short little 5.592 arc length. So I'm just adding up the remainder, because what I want to see is how close did my little arc lengths come up to the value of pi, and where is my error in that, if there is any. So then I add all that together, I come up with 3,141.5926,533. So I took the sum of all those arcs, these three little arcs, and subtracted that from the pi times 1,000, and the difference between those little adding up the arcs. Now remember, I'm just typing those in the calculator, so I don't have all the digits. But anyway, they're pretty close, 0.000000002366. So anyway, my error is just because on the calculator, these would all add up, because when you add those little arcs, they should be the full length of the whole circumference of the circle, which would be the pi times 1,000. All right. So, but basically what that did was that gave me, a value, just testing that out to see how that worked. All right. So what I want to do now is I really want to focus on the actual little short segment lengths that we have here, right? The segment that's below the arc length. So remember, we got two things here. We got the segments that added up all the way around, and we got the arc length that is above it. So what's the remainder of this segment here is 0.5921. That's the Q to D measurement. The arc length there is 0.5921. Sorry, this is just a very number heavy analysis, but I'm just trying to work through this myself, basically. So what I have over here is the 3,140 plus the 1, which is the P to Q measurement there, plus the Q1D measurement, and that comes up with 3,141.5921992217. Now that's when I just am adding up what these true values are of the arc, not the arc length, just the segment lengths. So these segment lengths, as I add them all the way up, this has nothing to do with the pi value at this point. It's just how many little segments did it take me to get back to D by just adding up the circles, right? And this little bit of remainder. And the value I come up with is 3.41592129917. So that whole value, I want to figure out, well, how close is that to pi times 1,000, which is this, pi times 1,000 minus this number of the added up little circles. So when I subtract this segment adding to this true value, the standard value of pi, I have zero. The difference between the two is 0.0052359. Now I assume that would be expected, because what's going on here is that the segment length has always got to be shorter than the arc length above it, because it's like a bow, right? Picture like an archery bow, right? So you got the big bow curve. Well, that's definitely longer than the segment of the string holding the two arms of the limbs together, right? So similarly here, we got that little arc length, which is just above the segment length. So there's not a huge difference between arc length and segment length. And just by calculating segment length alone, by this, using this one unit off of the 1,000 meter, there has to be a 1,000 unit diameter for this to kind of work out. So remember, 1,000 diameter is the diameter of this huge circle with these little units on it. But you see, it brings me back to 3.3141 units all the way across, 0.5921. And the only difference between that and the circle circumference above it, now using standard pi, is 0.000. But remember, the true debate here is I'm not trying to get the precise value of pi. What I want to know is like how close is the 3144 value compared to the 341. Remember, 3144 is still way over here, right? Because we still got to take that unit 1 and go way beyond it. Now, what is the difference between the actual arc length and the unit below it? Now, remember, this is the standard value of pi, so this is 0.521. So the difference between those two is this number down here. It's the K3 minus the Q1D measurement, and that's 0.0000000713. Now, even if this was 3.144, I think that the value of the difference in the arc length is still going to be way over here in the digits. It's not even going to touch the 3.144 measurement, or the 3.141 measurement between the arc length. So I don't know. This is what Geogebra and the values are telling me from just walking that circle around. And my approach, which I'm open to being terribly flawed here in how I'm going about this. But from what I could tell, it looks like that I'm ending up with something very close with just stepping circles around to 3.1415. And what's this last little equation that I did here? Oh, okay. So what I did here was I wanted to see the arc length, because it's saying arc length is just 0.0. So beyond the unit 1, it's 0.00000167. So that's how much is beyond unit 1, right? The remainder of that. So basically, if I take that number and I multiply it by 3,140, so I multiplied it by all the circles that got me to this point, the 3,140 of them, which is the arc length above it. How much does that add? Let's see, that adds up to, multiplying those values, it's only going to give me 0.000523438. So that's when you take this number and you multiply it 3,140 times, this is what you come up with in the end. And I must have taken that number, H3 plus P3, so that's this and this, minus this, 3,140.005235565 equals 0.0000125. So I guess I'm basically trying to determine here, when I take this number here, plus, okay, so I added that. Who knows what I did there? I'm not sure, but I should have taken better notes. Like I said, this is a little bit half-baked. I could get lost in the numbers a little bit, but this probably means something. But this was important for me to calculate, I know, because I wanted to see how much that value added up there. And this is the arc length measurement minus the arc length, H3 plus P3 minus this. Yeah, maybe I got confused. Whatever, it doesn't matter. So anyway, that's my kind of little summary of trying to work this out, which I understand if it kind of looks like a little bit of a mess here and figuring it out, because it's only been 2 days that I tried to determine this by using this method. So I'm curious, if I put this video up, what your thoughts are on this. And like I said, this is easy to draw in GeoGebra. Just do the 1,000 meter starting point starting segment, and then just create a circle and, create tiny little circles to get the 1,000 units, and then just start working your way around to do the complete diagram. Is you're not going to come up with probably too much different than what I've come up with on my results. Maybe some of the way far out digits will be different, but it's shockingly close to the value of pi, the standard value of pi, just by adding up those segments. Even if I don't account for any of the arc length stuff that I was just showing you, it's even on the other program that I showed, it's still coming up with roughly 3.1415. And I don't think that the segment length, the arc length segment above, is adding too much to the overall length to make it shockingly longer than 3.414, compared to 3.144, the golden pi. So, but we have Harry Lear's work on this, which looked very thorough, using physical measurements to the best of his ability with those tools to show that the value was greater than the standard value of pi. And that's super interesting to me. And, I guess one thing that I've learned after doing so much manual work with hand-drawn compass, or trying to do things by thinking, with my golden ratio calipers, or, trying to measure things by eye over the years and thinking that must be very close to pi, or very close, not pi, very close to a phi ratio measurement with the golden ratio calipers. I look at it, I'm like, oh, that's golden ratio. I measure with the calipers, and I'm like, oh, that looks like it's fine. And then I do go on a program like Geogebra or that Sketches app that I showed you, and I measure it, and it's not what my eyes are telling me. Even very precise measuring devices that I've had, just all that little manual manipulation, just always continues to add up to a lot of error. So maybe that's in Harry Lear's work, or maybe it's just so right on and we do have the value of pi wrong and it is related to golden ratio. Like I said, I think that would be great. I'd be very happy with that. Being in drawing sacred geometry, it fits right in, but at least from this little rough analysis that I did here, I still have a lot of questions about it. And from what I could tell, it looks like 3.141 standard value of pi seems to kind of work out with that technique that I showed. And so we've got some conflicting results there. And maybe it's just flawed from the beginning because it's on the computer programs, and it's already doing some sort of manipulation to the data that is not being factored in when you do it with real trust your senses, your actual eyes, rather than relying on to the mechanical devices to do that for us. But we're still using machinery and stuff to do all that anyway. And measuring increments that have been fabricated in different locations that are trying to get their precision to top-notch accuracy, which probably uses some program that may be related to pi. I don't know. It's a crazy circle and loop, but I know I'm rambling here. But I hope you enjoyed that. And like I said, very different video. I'm not tied to absolute facts on this one for sure. Just like I said, kind of little rabbit hole I went down, and I'm following up on the heels of this recent video that I did to expand it and explore a little more. All right, well, thanks for watching, and check out the new geometry courses. I don't have anything really related to this on there. This is just an open discovery and discussion kind of topic. So yeah, much love and appreciation, and we'll come back with another video hopefully soon. Bye.